Welcome to a screencast on the dissolution process. The objectives for this screencast are for you to be able to describe the basic components and properties of solution and how and why solutions form, and to be able to describe the molecular properties that affect solubility, to predict whether a given mixture will yield a solution, and to predict the relative solubility of different solutes and solvents. Now, first of all, what makes something a solution? Well, in general, a solution consists of a solute dissolved in a solvent. Typically, the solute is what we have less of, and here we're representing that by these red spheres representing solute particles, and that is dissolved in a solvent. The solvent we typically have more of, and here it's represented by the blue substance surrounding the solute particles, and the solvent individual molecules are not being shown here. And in a solution, the solute particles are the size of typical ions or small molecules. And solutions are homogeneous mixtures of solute and solvent. Now, there are also other kinds of mixtures known as colloids and suspensions. Those have larger particles of solute, and here we're going to focus on solutions. Now, a specific solution will have properties that depend, of course, on the specific solute and the specific solvent. But the solution also has properties that depend upon the concentration of the solution. If we have a lower concentration or more dissolved particles per amount of volume of solution, so higher concentration, that will affect properties of the solution as well, and we'll look at that in more detail later on. Now, solutions form spontaneously, and what this means is they form without needing any added energy from an external source. We can maybe make a solution form more quickly by stirring or adding heat by adding some external energy, but the solution itself doesn't require that. It will form spontaneously without needing the added energy. Solution formation is favored by two main factors. One is decrease in internal energy of the system, and the other is increase in disorder of the system. And for solution formation to occur, either the internal energy of the system needs to decrease, or the disorder of the system needs to increase, or very possibly both of those might occur. And this turns out to be generally true of spontaneous processes, and we'll look at that in more detail later in the course as well. Now, an example of solution formation is potassium chloride, an ionic compound dissolving in water, a polar solvent. And basically, we have the solution occurring because potassium and chloride ions attract each other via the ionic bond or by positive-negative attraction. Water molecules are polar. They attract each other via dipole-dipole attractions, and in fact they have hydrogen bonding, a particularly strong type of dipole-dipole attraction. And if we have some potassium chloride and we add to it some water, then the negative side of the water molecules, the oxygen side is slightly negatively charged, will attract positive ions. And the positive side of the water molecule, the hydrogen side, is slightly positively charged. That will attract negative ions. And if there's sufficient attraction between water molecules and a positive ion or a negative ion, if we have strong enough ion-dipole attractions, then that can overcome the ion-ion attractions, the ionic bond between potassium and chloride ions, and in a sense the potassium and chloride ions are pulled into solution by the polar water molecules. So this particular process occurring, this solution forming, has everything to do with intermolecular attractions, attractions on an atomic or molecular level, and their relative types and strengths. And in general, this is kind of what's going on, or things we have to look at in terms of solubility. The solubility of a particular solution depends upon the relative types and strengths of the intermolecular attractions between solute-solute particles, so how strongly they attract each other, solvent-solvent particles, how strongly they attract each other, and then the solution contains solute and solvent, so how strongly solute and solvent attract each other. And in fact, we can think of solution formation as sort of a hypothetical three-step process. Here we're representing solute particles by blue spheres, and if we have solute particles to make in a pure substance and we want to make a solution, the solute particles have to be pulled apart, separated a little bit from each other, enough to provide space for solvent particles to intersperse themselves. And then similarly, solvent particles, here they're represented by red spheres, need to be pulled a little bit apart from each other or separated a bit in the expanded solvent to allow space for solute particles to fit in and make a solution. And then, of course, once we've expanded the solute and expanded the solvent, then we can imagine putting them together in a mixture, in a solution, and now we have solute and solvent particles all mixed and next to each other. Now, of course, solution formation doesn't really occur via this three-step process. This is just a way to visualize it, but it helps us focus on the solute-solute attractions, the solvent-solvent attractions, and then when the solution forms, we then have solute-solvent attractions to consider. And what we find is when the type of intermolecular forces involved in solution formation are similar, in other words, if the solute-solute attractions and the solvent-solvent attractions are similar, then solutions will form. And here similar means similar type and relative strength of intermolecular attractions. And we have a more pithy way of saying this. The general rule we often state is like dissolves like. So if the solute and solvent have like or similar types of intermolecular attractions or intermolecular forces, then we would expect them to dissolve in each other. So let's end with an example of some possible solutions, and let's look at whether they form or not and the reasons why. So the first one is water, H2O, with ethanol, C2H5OH. Does this form a solution or not? And it does form a solution because water is a very polar molecule capable of hydrogen bonding. Ethanol has an OH group, which is a very polar, capable of hydrogen bonding group. So these have similar intermolecular forces, and so they do dissolve very well in each other because of that. What about water with hexane, C6H14? Does this form a solution or not? And this does not yield a solution because water is very polar, capable of hydrogen bonding. Hexane is a very nonpolar molecule, only has London dispersion, nonpolar attractions, and those are unlike or dissimilar intermolecular forces, so those don't form a solution. And then one more example. How about hexane with octane, C8H18? Does this yield a solution or not? And this does make a solution because hexane and octane both are very nonpolar molecules. They have similar intermolecular forces, so like dissolves like, they will make a solution. And that is it for the dissolution process screencast.